The STM32 microcontroller integrates encoder, IMU, ultrasonic, and infrared sensors while controlling both DC and servo motors, enabling precise navigation for Sonic. For straight line movement, two PID loops synchronize the DC motor using encoder feedback, while a separate PID loop controls the front rail servo for accurate yaw adjustments during turns based on IMU data. Ultrasonic and infrared sensor provide real-time obstacle detection, ensuring safe navigation. Additionally, the STM32 serves as the central communication hub, receiving movement commands from the Raspberry Pi via UART and executing them to guide Sonic's efficient and safe movement. Sonic, it's your turn. Head over to the Raspberry Pi team and let's see what they have in store.
For image recognition, we use YOLO V8, an object detection model, to recognize numbers and letters with varying backgrounds. We collected over 4,000 images, uploaded them into RobotFlow for annotation with bounding boxes, and split them into training, validation, and testing datasets. Once the model was trained, we set up a flash inference server. The RPi captures images and sends them to the server through an API. The YOLO V8 model processes the image and returns the predicted numbers or letters along with their corresponding bounding box coordinates. This setup allows for real-time image recognition with minimal processing on the RPi itself, making it both efficient and scalable.
RPi acts as the communication hub for all modules in the system. It connects to the STM32 microcontroller via USB, sending movement commands from the algorithm. It captures images through a camera, which are processed by the YOLO V8 server for real-time object detection. After receiving recognition results, it relays them back to the algorithm for the robot's next steps. The Pi also communicates with an Android tablet via Bluetooth, providing real-time status updates and ensuring smooth synchronization across the system. Sonic, back to you. Find out how to navigate the obstacle maze with the algorithm team.
Our algorithm guides Sonic through a 200 by 200 cm arena by combining the A-star search algorithm with a solution to the traveling salesman problem, while accounting for Sonic's turning radius and speed.
The A-star search algorithm calculates the shortest path from each target to every other target. The cost is calculated by combining Euclidean distance, penalties for changes in direction, and proximity to obstacles. Once computed, the optimal paths and their respective costs are stored.
Using the HELC algorithm, we can then solve the traveling salesman problem and determine the optimal order of targets. Sonic can then efficiently navigate to each target using the previously optimized paths and capture their images. Sonic, it's time. Let's head over to the Android team and see how they are applying our algorithm.
The main goal of the Android application was to facilitate communication between the users and the robot so that the movements of the robot could be controlled and the image ID of the images scanned by the robot could be retrieved. The application interacted with the RPi to send and receive commands from the robot and control the movements of the robot as needed. The home page displays a miniature version of the 2 meter by 2 meter grid and several features. The Place Robot button allows us to set the starting position of the robot. Obstacles can either be added by pressing the Set Obstacle button and choosing the square on the grid, or by keying in the coordinates of the obstacle and clicking Add Obstacle. Dragging an obstacle across the grid also changes the position of the obstacle, and dragging it out of the grid eliminates the obstacle completely. The Set Facing option can be clicked to change the direction of the image in each obstacle between up, down, left, and right. When Send Arena is clicked, the arrow representing the robot will move across the grid, mirroring the robot's movements.
The Bluetooth tab is used to connect the application to the robot. Turning the Bluetooth on and pressing search makes the tablet discoverable to other devices. The robot is then able to establish an African connection on channel 1 when a request to connect is sent via pressing the connect button. Thanks Sonic. Now, let's see you go full speed ahead and combine all the components together to complete our missions. Gotta go fast.
For mission 1, we have to program the robot to move through the arena on its own, recognize specific images on obstacles, and update the image ID in real time on our Android tablet. We have 6 minutes to complete this without any physical intervention, and points will be scored based on the accuracy of the image recognition. For mission 2, the objective is speed and precision. We start a robot in the car park and guide it to follow directional arrows around each obstacle. It must return to the car park autonomously and stop within 3 minutes. Timing stops only when the robot fully re-enters and stops in the car park.
Introducing Sonic, engineered for speed, precision, and unstoppable performance.